In the last video, we looked at a deadlock. In this video, I'll be showing you an example of a live lock. A live lock is when two or more threads are continuously reacting, each responding to the other's actions, and they can never successfully complete. You can find different examples of this problem on the internet. Let's say you and your friend have gone to an escape room. These are rooms where you have to solve problems to get out. In this case though, it's simply going to contain a maze you have to navigate through. You and your partner will start at different positions and have to find each other and aren't allowed to communicate with each other. Should you both look for each other? Definitely not, but the rules say each person must move within 3 seconds. In this video, I'll use a simple maze to demonstrate how you and your friend in the escape room's maze might be caught in a live lock scenario. I'll be creating a 4x4 maze and the paths are shown by the arrows. I'll have two people in the maze searching for each other, Grace and Adam. In this case, Grace is at position 1-1 and Adam is at position 3-3. Adam, if he moves to the next position, will go to position 0-0 or the top left corner. For the purposes of this code, the players must only move forward as shown. Getting back to the Thread Problems project, I'll create a new class in the dev.lpa package called maze. I'll set up a static constant, maze size. Since this is a constant, I'll make it uppercase. This maze will have a grid of cells. I'll set this up as a 2-dimensional array of cells, so my grid will be 4x4. Next, I'll add the constructor. This will be a no-args constructor. So just public maze here. In this constructor, I'll initialize all the values in the grid to an empty string. To do this, I'll loop through each row in my 2D array and fill each cell in that array with an empty string using arrays.fill. Next, I'll add a method that gets the next location for someone in the maze. You might imagine some algorithm here that's dependent on your maze configuration. In this case, I've made it simple and I'll just get the next cell in the grid, traversing over each cell and row one at a time. This method will take a cell location, so row and column coordinate pair, and I'll put that in an int array. This will return the next location as the same, an int array for the new coordinates. I'll initialize the next location, which I'll call next spot, to a new array of ints. If it's the last cell, then the player will be moved to the first cell. The row coordinate will be the same unless the cell was reset back to 0. If the row coordinate is 0 and the last spot was the last cell, then the position goes back to 0. I'll return the next spot from this method. Next, I'll add a method to move a person to another location. This method will take the location as well as the name. I'll set the cell to the first initial of the person who is moving in the maze. When a person moves in the maze, any work done by the partner searching for that person would need to be reset. I'll code the reset searched cells method next. I'll call this method reset searched cells and it will take a name. I'll loop through the rows. For all cells in the row, I'll replace any rows that have been searched back to unsearched or an empty string. When a cell has been searched, it'll have the not or exclamation mark and the initial of name, so any cells with these values will get reset. Let me show you what this code is doing on another slide. On this slide, the first grid shows the starting positions of both players. When Adam starts moving, the cell he's currently in can be said to not contain Grace, so I'll put a not G in that cell. In the second grid, Adam has moved 4 places from his original position at 3-3, and each cell he's searched so far, he hasn't found Grace. These are shown as grey cells and have not G in them, meaning Grace wasn't there. If Grace is searching and Adam is standing still, then we have the third grid. Grace started in position 1-1 and has moved to 2-1, and all the cells along her path are marked as not A because Adam wasn't there. This algorithm is only good if one player stays put. As soon as Grace starts moving, all of Adam's efforts will get erased, so all the cells he searched will get reset to unsearched and vice versa. So I've coded the reset search method before the search method, which I want to add now. This method returns a Boolean if the person being searched for is found in the next cell. So the arguments are the partner or person being searched for and the next spot and last spot. I'll check the value in the cell of the next spot, the spot this person would move to, and if it has the initial of the partner, then I know I've found the partner in this cell. In that case, I'll return true. Otherwise, I'll set the last spot to be the not symbol plus the partner's initial, and I'll return false. Finally, I want to override the toString method, so I'll do a Ctrl-O and select toString. I'll update this, and instead of returning serper.toString, I'll return the cells in the maze. I can do this by calling arrays.deep_toString, passing it the 2D cells array. Okay, so that does it for the maze class. Next, I'll create a maze runner class, also in the dev.lpa package, and I'll include PSVM there to get a main method. I'll include a couple of extra types in this source file. The first will be a participant record. This record has a name, the searching for string, which is the partner's name. It will also take a maze and an integer array, the starting position. I'll create a compact constructor. This is just going to set the participation's location on the maze. That's all I need for the participant record. Next, because I need data from this participant to execute the search, I'll create a thread class. I'll do this right after this record and call it participant thread. I'll have this class extend the thread class. I need a constructor to set the value of this field, so I'll generate that using alt-insert. In the first dialog, I'll select the thread with no arguments. And on the second dialog, I'll take the default, so the participant. Since I want my thread to have the same name as my participant, I'll chain a call to the thread serper constructor. I'll pass the participant's name to that. Now, I need to override the run method. I'll just do this manually. I'll include the override annotation. The signature is public void run. I'll set a variable, last spot, to the participant's starting position. I'll assign the maze to a variable as well, just to make the code easier to read. I'll start a while loop that will continue to run until a successful search has been done. I'll get the next location based on the last spot of my participant. I'll print that the participant is searching and print the maze. Between getting the new spot and the println statement, I need to actually add the code that does the searching. I need a try clause because I'll be using thread.sleep. I want this thread to pause a half a second before its next search. I'll call the search cell method on the maze, passing the name of the person this thread should be looking for. I'll also pass the new spot or position in the last spot. If this method returns a true, I'll print out information about the successful search, like the person doing the search, the person they're looking for, and the position they were found at. Once the person is found, this thread can stop running, so I'll break out of this while loop. Here, I'll add a synchronized block on the shared maze because move location is going to change the maze values. If no match was made, then this player will move to the next location, which I'll get by calling maze.moveLocation. I'll save off the last spot. I need the usual catch block. This time though, I'll reassert the interrupt. Without this, the thread may not be properly interrupted. I'll return from this code if this happens. Okay, now I've got all the parts to run this thing. I'll instantiate a new maze. I'll create a new participant, Adam, whose name is Adam, and his partner, or the person he'll be searching for, is Grace. I'll pass the maze and Adam's position in the maze. The next participant will be Grace, searching for Adam and her position. I'll run this so you can see what the maze looks like at the start. From this output, you can see the entire grid printed as a two-dimensional array on a single line of output. You can see that Grace is in the second row and the second cell, which is 1, 1, and Adam is in the last cell of the grid, 3, 3. To help you understand what this code is doing, I'll run each thread on its own first. For this example, I'll use my own advice and use an executor service to manage these threads. I'll get a cached thread pool from the executors class. I want to check the status of the running threads, so I'll use executor.submit. Remember, this method returns a future, so I'll assign that to a variable called Adam's results. I'll pass this method a new participant thread created with my Adam participant. I need to call shutdown on my executor. I'll run this. You can see the thread working, printing that Adam is searching. Adam started at the last cell in the grid, and obviously Grace wasn't there, so this was marked as not G, and Adam was moved to the first cell in the grid. Each time Adam moves, the cell he was in, he can mark that Grace wasn't there. This continues until he actually gets to the cell where Grace is. At that point, the thread prints that Adam found Grace and gives her position, and the thread stops running. I'll comment out that submit statement. I'll execute the next thread with Grace as the participant. I'll run this. Now, the thread has Grace searching, and you can see the G moving through the grid. Each cell she was at previously marked as not A, meaning Adam wasn't there. And she too eventually manages to find Adam. This code works great when the person being searched for never moves. But what happens when they do? If Grace is looking for Adam and he moves to another cell, it's a valid statement to say that all her previous work is useless. She cannot say with any certainty, after he moves, that the cell she looked in previously Adam free. That's why my maze reset will reset all cells that have a not A in them if Adam moves. And it'll do the same if Grace moves, invalidating or removing the not G setting in this maze. Let's run our two searching participants asynchronously. I'll uncomment the submit statement that kicks off Adam's searching. Before I run this, I'll set up the situation that if one thread completes, it will shut down the other. I'll set up a while loop that will check both Adam's results and Grace's results. If both return false from the isDone method, that means they're still running. I need a try block, so I can call thread.sleep for 1 second. And the usual catch goes here. If I get to this point, then one of the threads was successful and the other thread should stop searching. So if Adam is done, I'll cancel Grace's thread, passing true to the cancel method, which means I want the currently running thread to be interrupted. I'll do the same thing in reverse if Grace is done, cancelling Adam's search. Okay, let's try this out. I'll run this. And I'll let this run for about 20 or 25 statements, then I'll quit the application. You can see now that Adam and Grace are both searching for each other and they're both on the move. The threads are active. Each thread is changing the state of the maze, which means each thread keeps searching and will keep searching indefinitely because each is moving linearly, always away from each other and at the same pace. I've created a live lock. My threads aren't blocked, they're just continually working, responding to the maze's state that was changed by another thread in a loop that may never end. Actually, you can have this problem without locking. I'll comment out the synchronized block for a moment. I'll rerun this. And you can see I get the same situation. In actuality, the locking code might have a better shot of getting out of the live lock. If one thread might block for a little bit waiting on the lock, then the other thread might be able to move closer to success. I'll kill this again. I'm going to revert the last change where I commented out the synchronization code. Live locks can be difficult to debug and fix. For this reason, there are a few general things you can do to avoid them. Avoid having threads that are constantly checking each other's states. If possible, design your code so that threads can make progress independently of each other. Use timeouts to prevent threads from waiting indefinitely for each other. Use randomization to break the symmetry between threads. For example, if two threads are both trying to acquire the same resource, you can have them randomly decide which thread should acquire the resource first. As I've demonstrated, the problem in this code isn't due to the synchronization code or locks. One solution which might help is to execute the search, but randomize the search time a little bit. In this code, our partners are sort of in lockstep, both moving forward at the exact same rate. Let's have each thread wait a different amount of time. You wouldn't hard code this in a real game, but I'll just do it here to make the result more consistent than trying a purely random solution. I use a ternary operator. If the name is Grace, I'll wait 2,900 milliseconds, otherwise it will only wait 500 milliseconds. I'll run the code with this change. Since Grace is waiting almost all the way up to the 3-second max and Adam is moving every half a second, he's able to catch her. Obviously, in an application maze, this code isn't the right solution. You could even argue a live lock here makes the game more challenging. Still, I hope you were able to see from this example that one thread's actions can affect another thread in such a way that completing the tasks is nearly impossible. That's a live lock in a nutshell. In the next video, I'll talk about the third common threading problem, starvation, so I'll see you in that next video.